Section 11 is going to introduce the final solving technique that we have for systems of linear equations. This is going to be known as Kramer's rule. Before we can discuss Kramer's rule in any detail, I have to first give you the information about another calculation called the determinant. In the previous section, section 10, we were giving an introduction to what the matrix structure was all about. And we did some calculations with matrices such as the summation, the difference, scalar product, and then we used those in solving of a matrix equation as well. So there's going to be another operation that I want you to be able to do called the determinant. So associated with every square matrix is a real number called its determinant. And we are going to be focusing on 2 by 2 square matrices. We are not going to be using any 3 by 3 matrices in this course, or 4 by 4, nothing higher than that, of course. We're going to be focusing on just 2 by 2 matrices. So we are really going to only be applying Kramer's rule to systems of linear equations with 2 variables and 2 equations. We're not going to apply this to the 3 variable, 3 equation situation that we had back in section 9. So definition 11.1 is going to tell you how to calculate the determinant of the 2 by 2 matrix. So it says here the determinant of the 2 by 2 matrix A is, and then there's the calculation. So the calculation is right here. This is the formula that you need to be able to calculate the 2 by 2 determinant. Everything else is going to be ways of indicating that you should be taking the determinant. So you can use the abbreviation DET, where it says determinant of A. Sort of like when we do function notation. With function notation, we call this f of x. It's not meant to be called f times x, but f of x. So this is kind of the same thing. It's the determinant of A, or maybe a better analogy for that would be the domain of f. It doesn't mean d times f, it just means the domain of whatever is on the inside of the parentheses. So that's what's going on here. This is the determinant of matrix A. And then the second notation, which is equivalent, this one right here, it uses what looks like absolute value bars. But at this point, you should realize that mathematicians reuse notation all the time. So the symbols for the absolute value are what are here, but it doesn't mean absolute value. What it means is determinant of, and then whatever's in between the absolute value brackets means that's what you're taking the determinant of. So it means determinant of matrix A. So you have to be careful about context in terms of whether to interpret this as an absolute value or whether you interpret it as a determinant of something. And then certainly you can take the actual entries themselves, and instead of using capital A as the representative for the matrix, you can just actually have the entries there and stick them in between your absolute value bars, which means take the determinant of, and then you've got your 4 entries there. So the formula is really what we need, so that way we can move forward with actually doing some of these calculations. So the formula says that we're going to multiply A times D. So that's the 1, 1 entry multiplied with the 2, 2 entry. And then it also has a multiplication with BC. So that's the 1, 2 entry multiplied with the 2, 1 entry. And the order of this is really important because we have subtraction in between these 2 products. If you switch the order of your product within the subtraction, you will get the opposite answer of what you're really supposed to get. So please make sure that you put the AD product first minus the BC product second.